Hey there, welcome back to the Science Hutch. I'm Hutch, and our very special science is looking at a projectile puzzle where we have R2-D2 flying through the air as a projectile in two-dimensional motion, and we are about to look at what are the kinematics equations that will help us to solve projectile puzzles, and how can we use those kinematics equations to solve projectile puzzles. So I have the puzzle right here on my iPad, and let's take a look right now.
At this point, R2D2 is going to land on the ground 47.6 meters away from where he was spit out. But how long does that take? What is R2D2's hang time in the air? So we're going to pick up in the guess method here. We just got our givens written out. We've got our unknown established, and we want an equation that connects these. Now, here I'm going to teach you the kinematics equations. We're going to take a little sidebar into the kinematics equations. If you already know what they are, then you can go ahead and skip forward to see the solution. But this is for those of us who are learning two-dimensional kinematics fresh and new. In kinematics, there are really 5 different variables to keep track of. We have the initial position, the final position, but most of the time we're just going to combine those two into one variable that we'll call displacement, where we're looking at the change in those two positions. The change in anything is really the way that that thing ends up, or the final, put an X subscript F for final, the final position, the difference between that final position and the initial position, or the position at time 0, or X sub 0, or X sub naught. N-A-U-G-H-T is naught, and it means 0. If you say the word difference in English, in mathematical language, you're saying subtract. Take the difference between two things, subtract them, and see how they're different, right? So this is displacement. Displacement is our first real variable that we look at in our kinematics equations. And then we have, well, how quickly did you displace yourself? How quickly did you move from one place to another? And that is your velocity. Now, for velocity, because we have constant acceleration, and acceleration is change in velocity, we are going to need to consider initial velocity and final velocity. This is initial velocity and final. Oops, initial. More eyes. We need more eyes in there. And then we have the constant acceleration that's happening. And remember, acceleration is defined as a change in velocity happening in a certain amount of time, or a change in time. And remember that change in anything is the difference between the final and the initial state of that thing. So that would be VF minus V naught over a change in time. I'm going to come back to that in a minute. We're going to use that to create like one of our kinematics equations. And then the last thing we have is that change in time. You can call it change in time. You can call it time interval. Sometimes they'll just say the amount of time in seconds. We always measured it in seconds. Right. So now let's create some equations that connect these things.
The first kinematics equation we're going to collect is going to have final velocity, V sub F, equals initial velocity, V sub naught or V sub 0, plus acceleration times our change in time. And remember, I'm using a delta for the change in symbol. And the second kinematics equation is going to have a lot of 2's in it. It's going to have VF squared equals V naught squared plus 2 times acceleration times change in position or displacement. So we X'd out the time here, and now we have displacement in our equation. And then the third one we're going to use is going to have displacement right at the front of the equation. Everything else is going to be set equal to it, and it's going to be displacement, or delta X, equals initial velocity times change in time plus 1/2 times acceleration times change in time squared. Okay, and now we can create a fourth one with this nice little relationship that we have that talks about what is an average. How do you take an average of two things? So let's say that we want a kinematics equation that does not have acceleration. See, all of these equations have acceleration in them. So what if we don't have acceleration? We don't want acceleration, but we know that there is a constant acceleration. So we just don't know what it is, and we don't care about finding it. So here's an equation that can help us out with that. So let's look at what is VAVG. Subscript AVG I'm using for the word average. So what is an average velocity? Well, to get an average velocity, you can just take displacement divided by time. So the total displacement divided by the total time. But also to get an average of two things, you just add them together and divide by 2, right? That's a mathematical average, taking a mean average. So we have two things. We have an initial velocity and a final velocity. So what if we said, all right, so final velocity plus initial velocity, sorry, these are terrible V's, and then divide by 2. Okay, and now we can just take out the middle part here, and we can just put these equal to each other. And then if we want to just set the whole thing equal to displacement, we can multiply both sides by change in time. Put a big parentheses around that. Multiply that whole side by change in time. And then what happens on the left? Well, change in time and change in time, they cancel with each other. So we get to get rid of them completely. And now we have a fourth kinematics equation that allows us to have a kinematics equation that's reliant on there being constant acceleration, but acceleration does not show up in the equation. And that's nice because if we look carefully at all 4 of our equations, we can start seeing some cool things here. Like, why would you need 4 equations? It really looks like, you're kind of repeating what you're saying here. But let's make a little table together to see why. Why would you need 4 equations? Okay, well, here's the deal, friends. Here's a little table. La, la, la. La, da, da. La, da, da. Okay, so let's say what is missing. What is missing here? So what is missing in each of these 4 equations? Well, we have 5 variables to work with. All right, we have displacement, initial velocity, final velocity, acceleration, and change in time. So what is missing in each of these equations? In the first one, we have final velocity, we have initial velocity, we have acceleration, and we have change in time. But we don't have displacement. So what's missing there is displacement. And then in the second one, we have final velocity, initial velocity, acceleration, but now we've replaced time with displacement. So we do have displacement, but we don't have time. So now we're missing change in time here. And then the third equation, we have displacement again. We have time. It shows up in 2 places, actually. We have acceleration, and we have initial velocity. So who was knocked out? Well, see, final velocity was there in the first 2 equations, but now final velocity is knocked out by displacement. So final velocity is missing here, V sub F. And then the last one here, well, this is, we talked about this already, it's acceleration, right? We did that whole work just to get rid of the acceleration, so that would be the missing variable here. Now, why do we care about going through that process? Well, that's actually going to be really helpful to us to figure out how we are going to choose our kinematics equation to solve a puzzle. So here's the key. When you're choosing a kinematics equation, you look at your givens and your unknown, and you list out what you have and what you don't have, and then you will usually have 3 things. You'll want to get the 4th one, and so that's 4 variables out of our 5. The 5th one will be like not ever even mentioned. You won't want it, you won't have it, and that 5th one, that 5th variable, is actually how you choose your kinematics equation, because you look for the equation here that is missing that 5th thing. And so you can plug in values for your first 3 givens and solve for your unknown variable. Let me show you an example here as we get into our R2D2 puzzle. We're looking at part B. Part B says, how long is R2D2 in the air? So how much time is R2D2 in the air for? There's another step to solving these puzzles that can save you a lot of heartache. The first thing you want to do is you want to ask yourself, what dimension should I work in right now? Should I work in the horizontal dimension or the vertical dimension? This puzzle is asking about change in time. Change in time equals how many seconds? Now, change in time is independent of three-dimensional space. It's its own dimension of time. So that means that you can choose. If you can solve for it horizontally, go for that, because those are easier equations. Really, for a projectile, the only equation horizontally that you need is average velocity equals your total displacement over your total time. Total time is what we're interested in. This is how long R2D2 is in the air for the entire trip. So we can use this equation here, and we don't have to even worry about picking any of the kinematics equations. Why? Because we already have this information. So where is this information? Let's go look at our givens table. We have displacement, 47.6 meters forward. We have an initial x velocity, which is going to be the launch velocity times cosine of that angle that R2D2 was launched at. So it's going to be 22.5 meters per second times cosine of 35 degrees. And that's all we need, folks, to get the time, because here is our horizontal velocity, v sub x, and that is going to be the initial velocity times cosine of the launch angle, and then displacement over change in time. And we know everything to plug in here. So our initial velocity was at 22.5 meters per second. I'll put parentheses around that to make it nice and cozy, times cosine of 35 degrees, parentheses, equals displacement is 47.6 meters divided by change in time. So the only thing we don't know is change in time. We can just solve for it using our sweet algebra skills. Let's just go ahead and multiply both sides by delta t. Da, 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 da. Wow, wow, huge parentheses around all that. It's getting a little messy. Let me grab this and move it around a little bit. La, da, 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 da. Oh, I got the box. Oh, wow, that's fine. We will get rid of the box. Ha! Now, what happens over on the right side? Well, oh, my friends, the change in times cancel each other out, so they are gone. Let's go ahead and get rid of them. La, 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 la. Okay, and then now what do we do? Well, algebraically, we can divide both sides by all of this mess, 22.5 meters per second times cosine of 35 degrees. And then let's keep all the parentheses just to be nice. I'm getting tired of writing all this. Let's go ahead and crunch that number out. 22.5 times cosine of 35 degrees is 18.4 meters per second. Oh man, I'm so amazing. No, I used a calculator earlier. All of that stuff is 18.4. And I'm just going to bring the units down with it, meters per second. And then this is 18.4 meters per second. Divide that off on both sides. All of that is 18.4 meters per second, 18.4 meters per second. And then all of that cancels out. And what do we got? This is what we got. Boom. It's going to be 2.6 meters, and meters are going to cancel. Then you're dividing by seconds. So those divide by really means multiply. So we're going to have 2.6 seconds. So that's our time, right? That's our answer. I wrote it out the long way for you to show you all the algebra. I didn't want to skip a step or whatever. But in the future, friends, this is what you can do. When you have a situation like this, you can totally swap that with that. You're totally allowed to, okay? So here's how that works out. Ta-da! And then, okay. This is what happened. Answer. Yay. All right, good times. Let the good times roll. Sweet. So that's the easy one. So again, the quick and fast way to answer these questions for yourself is number one, ask yourself, is this a X problem or a Y problem? If it's an X problem, then I can use most of the time that equation right there, because the horizontal situation for any projectile, the projectile is not accelerating forward or backwards. It's only accelerating down. So that helps us not have to have a kinematics equation in play because there is no acceleration going on horizontally. So keep it horizontal if you can. But what if you can't? Oh boy, what if you can't? Okay, so now the next part of our puzzle is going to get a little bit tougher. So that was B. How long is R2D2 in the air? And the change in time again was 2.6 seconds. And you also want to ask yourself, does this make sense? Is this a fair amount of time to be in the air? If it was like a minute, no, that's way too long. But especially for just a situation where like you can watch R2D2 fly through the air and land. But if it's like about 2 seconds there, yeah, that's okay. That's all right. Okay, now what is the maximum height R2 reaches while in the air? Okay, now let this one, to save us some time, I've already written things out. So let me go over to my solution. Here's my solution. This is my handwritten work on it. And there we go. That's walking through the last puzzle. I'm going to switch to a laser pointer here. So how long is R2D2 in the air? My unknown was delta T. And I've already got my givens. I made my givens table here in the previous part. So I'm walking through the GUESS method, the guess method. I have my givens written out already. My unknown is delta T. My equation part, step one in my head, can I use the range equation? Well, no. Here's the range equation written out. And delta T is not even in the range equation. So I can't find delta T if it's not there. So no. So then my next question is, can I use an X problem because it's the fastest, quickest way? And the answer is yes. And that's what we just did. So there's my work walking through that process. Now, part C is going to be, what is the highest height that R2 reaches in flight? And height is a change in y, a vertical, we use y for the vertical, a vertical displacement. Now, what is the maximum vertical displacement? So the way I'm going to write that in a symbol is I'm going to say my new unknown, U for unknown, is delta y max. All right, my maximum vertical position or my maximum vertical displacement. And then I need an equation. So can I use the range equation, friends? Negatory. The range equation is for horizontal distances only. And this is a vertical thing I'm looking for. Can it be an X problem? Again, no, because height is a vertical situation. So I cannot use my horizontal average velocity equation. It's got to be a Y problem. Now, when it's a Y problem, here's my kinematics equations. So I've written them out for you. Boom, boom, boom. And then again, there is that fourth one. I don't usually use the fourth one in a vertical sense because the nice thing about a vertical projectile problem is that I always know the acceleration. So why not just have an equation that's going to have the acceleration in there? I always know that because it's going to be the acceleration of gravity for a vertical situation. So we're going to be able to substitute in lowercase g for our planet, which is going to be 10 meters per second squared if you don't mind rounding, or 9.81 meters per second squared if you do mind rounding. There are two ways to solve this. You can already see them laid out in my work here. And one thing I want to point out to you is here's you even now, after doing physics puzzles for a long time, I still draw my situation and it helps me get my head around what's going on. So this X marks the spot. That's just telling me this is where R2D2 is going to be at R2D2's maximum height. All right, his maximum height. And that's going to be at what it's going to take him 1/2 of the time to travel there, and then 1/2 of the time of the total flight to fall back down. So that's just me getting that there in my head. And the reason why I'm thinking that way is because I'm really going to plug in half of the time that I calculated in part B. So it takes him 2.6 seconds to travel the whole flight. Well, then it's only going to take half that time to get to the maximum height here. And so that's going to be half of 2.6, which is going to be 1.3. Yes, very good. Way to go. Way to math it. So 1.3 seconds. At 1.3 seconds, R2D2 will be at his maximum height. So I can pretty much kind of like program that in to the mathematics, and the mathematics will then spit out his vertical position for me at that time. You see, it's very much like plugging something into a computer program. And why? Because the computer programs are actually using these kinds of equations for us. So that's why it kind of works similarly, because the computer programs were made to work with this math that we're doing. So we're doing the original computer program stuff. We are the computer program right now. So here's the deal. Remember I said how we want to pick the equation based on what we don't have and we don't care about having? The missing variable? Okay, so let's review really quickly here. Out of our three kinematics equations here, what's missing? So we'll just throw it in here. So what's missing for this first one? Oh, yes, displacement. Now I'm working vertically, so I'm going to write a delta y instead of a delta x for verticals type stuff. So I should maybe even change this to a delta y just to be totally consistent, right? And then what are we missing in the second one? Well, we're missing change in time. And what are we missing in the third one? We're missing final velocity. Final velocity. The fourth one, which I didn't write here, remember we're missing acceleration. And then I can also be cool about the acceleration and know that that's kind of what we call a hidden given. It's not explicitly told to us because it doesn't need to be. It's hidden in the very fact that we already know a bit about the way physics works, and there is an acceleration of gravity working vertically on every projectile. And we know the acceleration of gravity value, so we can plug that in. So that's a given by default, or I say hidden given. Okay, so now let's see which equation we want. So number one, I can use two equations here. Why? Because by doing the different parts of the puzzle, I've collected new givens along the way, and that kind of opens up more options for me, which is pretty cool. So first of all, I know this initial velocity. I know g. And I know the change in time. So the first one is not going to work for me though, because like I'm looking for the delta y, the vertical position. So I can't find it. It's not even in this equation. So I can't use that one. But I do have enough information to solve for delta y in this equation. I will have my final velocity at my maximum height. And I'll tell you why. That's a hidden given. Another hidden given. What? Yeah. And then this one has my vertical displacement just already solved for. And so that one would probably be the most straightforward one to solve. So method number one is going to be where I'm going to take my equation here and I'm going to start plugging things in for it. So I'm going to have my delta y. I leave that as a variable. I don't know it. My initial velocity is going to be my vertical initial velocity. So vertical initial velocity is your initial velocity of your projectile times sine of your launch angle. So don't forget that. That's one of the most common mistakes that a lot of new physicists make. The other thing that I'm putting in here is 1/2 of my total flight time. If I plug that in to my equation there, it'll chunk out the position at that time. That's another reason why the picture is so awesome and helpful. And then I'm going to round my value of g to 10. Now, watch your directions, right? So we have up and down, so we can have a plus and a minus direction. And up is going to be plus for me, minus is going to be down. So my direction has to be negative here. I have to have a negative 10 meters per second squared because gravity is pointed down. So make sure you plug that in, otherwise you'll be doing a plus once you get to this point, and that plus will give you the complete wrong answer. All right, and so then we're going to plug in our values here. Initial velocity of 22.5 meters per second times sine of 35 degrees is going to give you 12.9. Then here's my total time I found in part B. And then I'm going to do 1/2 of 10, which is, or 1/2 of -10, which is -5 or -5. And then I'm going to do my 1/2 of my total time again. And you boil the numbers down, 12.9 times 1/2 times 2.6 gives us this 16.77. And then 5 times 1/2 times 2.6. And watch out, it's the 1/2 times 2.6, then squared. All right, so it's really 1.3 squared, then multiply by 5. So just watch your order of operations. If you do that right, you'll get 8.45 meters. And what's going on? How are we getting meters out of this business? Well, what I really should have been, I should have been cool about writing my units everywhere. This is meters per second because this was a velocity. So meters per second is coming from that velocity. Meters per second times seconds. These seconds are going to cancel, and we're just going to get meters. So that's how we get meters from there. And then over on the right, this is really 2.6 seconds, right? Now that ends up being, and let's just do a little sidebar here. This ends up being essentially, without the numbers, what's happening with the units? Meters per second squared for an acceleration. Those are getting multiplied by seconds squared here. Second squared over 1, essentially. But now the seconds then again are going to cancel. The second squared cancel with second squared. And now again, you're just going to end up with meters, which is where those meters come from. And what's nice about that then is this equation is valid because we're adding like terms. We're adding meters to meters. We're really subtracting meters from meters. And for those of you who like to know why you're doing the math you're doing, okay, this first bit here, this bit says this is how far up the projectile will go if you launch it at this speed and give it this much time to travel upward, okay? And then the second bit here, this subtracting bit, this is how much effect gravity has on it during that amount of time. So you're going to plug in the strength of gravity, which is the -10, and then you're going to look at how much time it has to work on the projectile. And that's also why it's important to put a negative, because it's working against the projectile's motion to get it to stop at the top of the flight and come back down. So that's kind of why those two pieces are there. And that's why you end up having a subtraction. So this is how high R2-D2 would be in the sky if there were no gravity on Dagobah. And then this is how much gravity has brought R2-D2 down from that height at this point in time. And so that is as high as R2-D2 will ever get, 8.3 meters. All right, all that fun little squiggly squaggly stuff. Let's get rid of it all there. Now, the other way to work this is to see the hidden given. Now, watch what happens here. Okay, at the highest point in a projectile's flight, what is your velocity vertically here? Your v sub y. Well, it's right here. It's 0, okay? V sub y equals 0 meters per second, just for an instant. Not its horizontal velocity. It's still moving forward at the same speed it always has been since it was launched. But it's got to stop at the top so it can start to fall back down just for that instant. And that's amazing. That's a hidden given. And you can set that to your final velocity. So whatever velocity is your initial y velocity, that has been reduced down to 0 at this moment here, and now you have 0. So you're just working the puzzle from this moment to this moment. All right, just those two moments there. And that's fine. You plug that in as your final moment, and you get some awesome, easy physics going on. Okay, so it's a great way to be smart about your physics. So we're going to plug in our final velocity as 0 at the top of the maximum. You can do that for every projectile at its maximum height. Its final velocity will be 0 as long as it's just like launched up and then coming back down. And then we're going to put in for our initial velocity, it was the launch velocity times sine of theta. Like if it helps you to keep separate like v sub 0 and v sub 0 times sine of theta, put a little extra y subscript so you know your initial y velocity. You can also do that here. If you really like subscripts and you want to label a lot, That's great. Nothing wrong with that. And then we're going to have our acceleration of gravity times 2. So it's going to go from 10 to 20. That's why we see our 20 here. And then we're going to solve for our maximum displacement. And we should get the same answer. So this is kind of cool. We can do a different equation, plug in the numbers, and we should get the same value so we can double check our work. And I do. I get 8.33 meters high. And here I got 8.3 meters. And there's only a difference in significant digits, but it's the same height. So that's pretty great. Okay, and the next part of our puzzle is going to be where we are going to look at where does R2-D2 reach maximum height? Well, because everything is symmetrical with the flight here, R2-D2 is going to reach maximum height at exactly 1/2 of R2-D2's total range, or horizontal distance traveled. So just multiply R2-D2's total distance traveled forward by 1/2, and you've got it. So at 1/2 of 47.6 meters is 23.8 meters. So that was a quick and easy one, huh? We got off on an easy one there. And now we're going to take it up to a whole other level. So now we're going to look at, okay, we're going to get a height for Luke Skywalker. Luke Skywalker standing on the shore like R2, and we're going to see if R2 is going to hit Luke or fly over Luke's head. Like, was the swamp monster under the water with R2 in its mouth like, oh, I see that guy, and I'm going to like, and like spit R2 as a projectile like into Luke? I don't know. We don't know if this swamp monster is an intelligent being who would think that far ahead, but does that happen? Well, let's use physics to find out. Now, if you watch the movie, you know what happens in the movie, but we're going to do this with the numbers we have right now to see if these numbers are consistent with what we see in the movie. Okay, so here's what we're given. We're given G, we're given the delta Y of Luke Skywalker, the height of Luke Skywalker. Okay, so the top of his head is 1.83 meters high. We're saying that Luke Skywalker is 6 feet tall. And then we're looking at the horizontal position of Luke Skywalker from where R2-D2 is spit out of the water. So that is the horizontal displacement, the distance along the ground that Luke is from R2-D2, where R2-D2 is launched from initially, which is 2.44 meters. And that's all given to us. And so then, so now the question is, will R2-D2 fly over Luke's head? So we want to find out, and again, pictures are super helpful. We want to find out if R2-D2 is going to be at a higher height here than Luke is. Okay, if R2-D2 is at a lower height, then R2-D2 is going to go right into Luke. If R2-D2 is at a higher height, then he's going right over Luke. So that's what we're looking for. So Luke's height is not going to be a given that we use to calculate anything about R2-D2, because R2-D2's flight as a projectile has nothing to do with how tall Luke Skywalker is. So we're not going to use Luke's height to calculate anything. We're going to use it to compare. Once we find out how high off the ground is R2-D2, so what is the delta Y of R2 at this location? All right, so once R2 has traveled forward this far of 2.44 meters, how high off the ground is R2-D2? That's what we're really looking for. Okay, so can we use the range equation? Step 1, no, because we're not landing at the same height that we were fired from. Level ground, we don't have it. We're looking at a point where R2-D2 is still up in the air at some height. Can we use a horizontal problem? Is this an X problem? Let's see. We have a horizontal distance, but we would need horizontal velocity, v sub x, which we can get with remember, v sub 0 times cosine of theta. We can totally get that. We know that. And we have a displacement of 2.44 meters. So those are givens for us. And the other thing we need for our equation, v sub x equals total displacement over total time, is time. So at what point in time will R2-D2 be at Luke? Now,
Do I care about that? Well, that's not what I'm being asked. I'm not saying like how old is Luke or at what point in time does R2D2 get to Luke. I'm looking at how high is R2D2. So a height is going to require a vertical situation. But keep the time in your back of your mind because we're going to see this is an advanced puzzle. This is what I call a two-parter. What? A two-parter? Yeah. So here is my givens table. So here's my givens for R2D2. Remember, I'm not looking at givens for Luke, and I'm being careful about differentiating vertical and horizontal. All right. So y is vertical, x is horizontal. Initial velocities for both of them, final velocity. Now the final velocity doesn't change from the horizontal, right? So that's why I wrote the same value for both. There's no acceleration horizontally for any projectile. And then we know this is hidden given for vertical acceleration for projectile of gravity. And we know how far forward R2D2 will travel, but we don't know how high R2D2 will be. And so this is our unknown that we're solving for. And then we also don't know how much time is going to go by from when R2D2 is spit out of the water till when R2D2 is at Luke's location. Do we want that? I don't know, but we don't know it. So I left it as a question mark. We also don't know how quickly R2D2 is moving up and down in the air. We don't even know if R2D2 is coming back down or if he's still rising. All right. So then we're solving for a vertical position. So we should say this is a vertical or a y problem. So we're going to go for that. We're going to go look at it as a y problem. And so here we are. Here's my y problem. Remember that red stuff is where I was talking about if it was an x problem. Leave that alone for now. And my y problem, my question is, okay, out of my kinematics equations, which one's going to work? Well, if I look at my kinematics equations, I look for the kinematics equation that is going to have the three things vertically that I have: initial velocity, acceleration. Wait a minute, I don't have three things. I don't have three things. Oh no, what am I gonna do? I guess I gotta give up. I guess there's no way to solve this puzzle. No, sir. No, ma'am. No, them. This is solvable. This is a two-parter, people. Here's the deal. You got to leave this first bit a little unfinished. So I do know I can find my initial y velocity, and it's 12.9 meters per second. Once you put in your 22.5 times your sine of 35, you get 22.9. That's fine. I know my acceleration of gravity is 10, and I can do 1/2 of 10, which is my 5. Remember, I put my minus in because it's pointed down, and that's the direction. But I don't know t, and now I don't know y. So this is as far as I can go, right? So I know I don't know t. Aha! But, remember up here where I was like, is this an x problem? Well, I could solve it. I could find t with the x. Yes, yes. So I can find t with the x. So we're going to be tenacious. We're going to be aggressive. We're not going to quit. We're going to have endurance, and we're going to go find t with an x problem. Then we're going to come back to the vertical and plug t in and get our answer. And that's what you do, people. That's a twofer right there, two-parter. First part is go find t. So here's my average velocity equals displacement over time. And then I'm going to multiply time on both sides and divide both sides by horizontal velocity. And so that's why I end up with delta t equals delta x over v sub x. Plug in my delta x. I know that Luke is 2.44 meters away from where R2 is launched. So this is where R2 is going to be at this time. And then my horizontal velocity is my initial velocity times cosine of theta. And so then we're going to plug in our numbers. Divide 2.44 meters by 18.4 meters per second. And the meters again cancel, friends, and you end up with 0.13 seconds. So it's only been 0.13 seconds. It happens pretty quick. Like, could you react in a 1/10 of a second or a 13/100ths of a second to dodge R2D2? I don't know. I don't know. Now take that back to the Y problem, and we'll plug that in every time we had a T. So here's let me zoom out a little bit, right? So we can still see, here's my Y problem where I left it off. And I needed 12.9 meters per second times t minus 5 times t squared. So here's my 12.9 meters per second times t.
minus 5 times t squared. Doing your math. Okay, here's how the math goes. So you're going to multiply 12.9 times 0.13 in your calculator, and then do 0.13 squared, then multiply that by 5, and then subtract those two. Right? That's the correct order of operations. And if you do it right, you'll get 1.59 meters. Now, if you're watching this, I recommend you pause it right now and don't take my word for it. Never. So good scientists don't just take people's word for stuff. Good scientists are skeptical. We're skeptical. So that means we test things out for ourselves and we find out if what people are telling us is true. So I could be lying to you. You don't want that. So go find out. Use a calculator. Make sure you can do it yourself and see if I'm actually correct here. And if I'm not, write in the comments and let me know. I don't want to be putting this out there for everybody to be wrong. I'll fix it. Let me know. Thank you. Appreciate it. All right, back to our work here. Now, R2-D2 is going to be 1.59 meters up off the ground. So here's the ground. R2-D2 is like 1.59 meters up. Luke Skywalker is how tall? Luke Skywalker is 1.83 meters high. So R2-D2 is going to hit Luke. He's going to hit Luke. He's going to hit him somewhere because Luke is taller than R2-D2 is high in the air. So boom, they're going to collide. Now that's not what happens in the movie, but that's what happens in our physics. All right, everybody. Thank you so much for doing some physics with me here. Hopefully that was helpful. Hopefully you feel like you have a better strategy for approaching two-dimensional kinematics puzzles in physics. And we'll see you next time here on the Science Hutch. I was a Hutch, this was the science, and you're the physicist. So keep on physicsing.